Okay, solve y double plus 16y equals 0 given that, and then some boundary conditions. Okay, I hope you remember from the other example we did with this, anytime you have a differential equation containing the second derivative and the original, you should be thinking waves. The solution to this is probably some combination of sines and cosines. And so what we learned to use last time as our solution for this is a combination of a sine function and a cosine function. So this is our general solution, and you can make it work with this. Now, there's a shortcut, which I ignored when I did my first example, but I want to show it to you for this one because it eliminates some fairly major headaches. These frequencies are predictable from the differential equation, and you don't have to do a lot of work to get them, so it's well worth it. So the little a and the little b we can pick off fairly quick. And it goes like this. The coefficient in this differential equation on the y, this 16, they call that number k. So k is 16. It turns out both of these frequencies for this thing to work out have to be the square root of k. So k is 16. The square root of k is the square root of 16, which is simply 4. Both of these frequency numbers must be 4. So that's great. That's two parameters we don't have to fight for very hard. Those are both just 4s. Wonderful. Okay, so what else can we get out of this thing? They say when x is pi by 2, meaning 90 degrees, y equals 1. So when x is 90, y is 1. Well, we got an equation for y right here, so let's see what that tells us. Y equals big A sine 4 times x is 90 degrees. If you want to do this in radians, by all means, it's going to work the same. I find degrees a little more comfortable, so I'll go with those when I have the choice. Big B cosine 4 times 90 again. So this is 1 equals big A. 4 times 90 is 360 degrees, which is like 0 degrees. The sine of 0 degrees is 0. And then we get b times 360 again. The cosine of 360 is 1. So this cleans up to 1 equals b. And it doesn't tell us anything about big A, I'm afraid. We get a value for the capital B. I'm not sure if this means that the big A is 0 or that it's some other number we haven't discovered yet, but all we know for sure at the moment is big B is 1. So I'm going to circle back up to here, and where capital B was, oh, that's cute, I'll use that. That B value is 1, or actually, we don't even need a 1 there, we'll just say it's cosine 4x, that's good enough. So, we're learning more about our solution here. The only thing left is, what's this thing? Is there a coefficient on sine? Is it 0? Is it the square root of 2 or something? We'll find out shortly. The other information in this question that we have not used yet is this condition about the first derivative. So let's get our first derivative and see what it can tell us. If y is a sine 4x plus cosine 4x, then the first derivative, y prime, is, the derivative passes right through the big A. The derivative of sine is cosine 4x. And then from the chain rule, we get a 4 popping out of here, which I'm going to put out front. Then we get the derivative of cosine is negative sine 4x, and then a 4 pops out. So instead of plus negative, I'm going to put just minus and then that 4. Okay, so that's our first derivative, and they tell us when x is 90 degrees, that derivative equals 1. So the derivative is 1. We get 4 big A cosine 4 times 90 degrees minus 4 times the sine of 4 times 90 degrees. going a little faster because we've done this before. 1 equals 360 is like 0 degrees. The cosine of that is 1, so this is just 4a times 1. And for this term, we get sine 360, which is like sine 0, which is 0, so that whole term just vanishes. So 4a is 1, which means a is, hey, look at that. It is a mixture of both. So our solution up here, that mysterious capital A, turned out to be 1/4. The solution to this is a mixture of sine and cosine functions. They both have the same frequency, but it turns out they have different amplitudes.